This video is on mole conversions, and the learning target for today is understanding the mole and learning how to convert between moles, particles, and mass. So the first thing we want to understand is this periodic table right here. The periodic table that we have represents essentially a mole of each of these atoms and the masses of a mole of each of these atoms. So hydrogen. This is not this is not the mass of a single hydrogen atom. This is the mass of a mole of hydrogen atoms, which is 6.022 times 10 to the 23rd hydrogen atoms. So those masses are all masses of 1 mole, which is Avogadro's number of particles for each of those atoms. So that brings us to molar mass, which is the mass of a mole of a compound of any sort. So if you look at this is calcium chloride. It's got 2 chloride ions to every calcium ion. And so the molar mass is taken from the periodic table. And so you add up 1 calcium and 2 chloride ions, and you then, adding them up, you will get a molar mass of 110.98 grams per mole of calcium chloride. So take a second, and by the way, pause the video as you see fit as we go through this whole lesson, especially when we get to the practice problems. Pause it so that you get the chance to complete those problems first. So what is the mole? The mole is a counting unit. Just like a pair, a dozen, a ton, those are all counting units, and they represent a number. The number that a mole represents is 6.022 times 10 to the 23rd represented particles. And we say the word represented particles because it depends on what substance we're looking at. If we're looking at an ionic compound, the representative particle would be formula unit. If it's a single or an element, it is atoms. And then if it's a covalent compound, we say the word molecules. So here we have a covalent compound. It's water. Water, 1 molecule of water has 2 hydrogen atoms and 1 oxygen atom on a microscale. So you're looking at this tiny particle of water. Now, we don't usually represent things in microscales because we want to be able to measure it. So we do the macro scale. So a mole of water is what we like to use to measure amounts of particles in the laboratory. And so here you have a mole of water. And in a mole of water, there's 2 moles of hydrogen atoms and 1 mole of oxygen atom. So if you can imagine inside this container of water, which has a mass of 18.02 grams per 1 mole, inside this container, there's 6.022 times 10 to the 23rd water molecules. So get through that concept. Here's another idea that would help you. Here I have, in a balanced equation, we oftentimes see these coefficients as well as subscripts. So what this represents on a microscale is 2 molecules of carbon dioxide. And this is a visual way to see the 2 molecules of carbon dioxide, which means we have 2 carbon atoms and 4 oxygen atoms, according to this microscale drawing. Now, if we go macro, we go on a macro scale, there's too many for us to represent here. So the too many means that there's 1.2044 times 10 to the 24th molecules of carbon dioxide, which means we have 1.2044 times 10 to the 24th carbon atoms and twice that for oxygen atoms. So that's represented in the conversions that you see here. So there's 2 moles of carbon dioxide, which means there's 2 moles of carbon and 4 moles of oxygen. Again, too many for us to represent. So I put as many water molecules as I could put into that little area there. But we would see 1.2044 times 10 to the 24th carbon dioxide molecules if we wanted to represent the macro scale. So now it brings us to this little concept map. This concept map, I would recommend pausing it and drawing this because it helps you to know what you're converting and how you're converting it. So when you're going from particles to moles, you're really dealing with Avogadro's number, which is 6.022 times 10 to the 23rd. And then if you're going from moles to mass, you're using the molar mass from the periodic table. So this is a great concept map for you to be able to know how to maneuver. Notice the mole bridge between particles and mass. There's a bridge, and that's through moles. So let's start off with a really quick review on dimensional analysis. Dimensional analysis is basically converting from one unit of measurement to another unit of measurement. So here we have a simple example of 3 dozen roses, and we're trying to figure out how many roses that would be. So if I have 3.5 dozen, which is abbreviated DZ, roses, and I'm trying to get to the number of roses, what I would do is I would convert my dozen units to roses. So dozen roses to roses. And notice I'm labeling everything just to ensure that I know what that will guide me as far as my unit. And notice Mrs. No didn't put numbers in here because I'm really doing a dimensional analysis. And that's my important, that's the conceptual part of me being able to convert my units. So here I have 1 dozen, there's 12 roses. So this is my conversion factor. And this is always true. A dozen has always 12 of something. In this case, it's roses. So we don't need an S there. So multiplying these two numbers, you should get a value of 42 roses. So 42 roses is how to convert from dozen to roses. Now we go to the next one. Now we have 2.5 moles of roses. So we're using this counting unit called moles rather than dozen. And in the same light, we're taking this counting unit, which is represented by, in 1 mole of roses, there are 6.022 times 10 to the 23rd roses. That's a large number, right? And so when you multiply these two, you get a large number as a result. 1.5 times 10 to the 24th roses. So this is a quick review on how to do dimensional analysis. So let's actually do some chemistry dimensional analysis. And I'm going to present a couple of types of problems. Type 1 is moles to mass. And so the first thing we want to do is make sure we know what this compound magnesium bromide looks like. We're balancing or neutralizing our chemical formulas, our ionic formulas. So magnesium has a 2+ charge. Bromide has a -1. So the formula of this compound is MgBr2. A little review from the last unit. To find the molar mass of this compound, we'll need the periodic table. So taking the periodic table, we'll find magnesium and we'll find bromine here. So we add up all the masses of a mole of each of those atoms. Okay. So there's 2 moles of this, so we're going to double this, bromine, and then there's 1 mole of the magnesium. So working out the molar mass, you will then get a value that looks like this, where we see 24.31 represents the mass in 1 mole of magnesium. And then, of course, 79.90 represents the molar mass. I'm not going to put the units, but times that by 2 for bromine. And then add them all up together, you get 184.11 grams per mole of magnesium bromide. So now let's make the conversion between moles to mass. It could be, and so we'll need molar mass. So to do the mass to mole conversion, we start off with the given, which is 0.760 moles. And we're going to convert it to grams. So moles on the bottom of magnesium bromide, noticing I'm analyzing the units, and then grams on the top of magnesium bromide. So in 1 mole, there's 184.11 grams. Multiplying that through, cross-canceling your units, your dimensions, and you'll end up with a value of 140 with a dot at the end, because there's 3 sig fig here, grams of magnesium bromide. Okay. Now we go to type 2 problems. Type 2 problems. In type 2 problems, we're looking at copper 2 nitrate and converting grams of copper 2 nitrate into moles of copper 2 nitrate. So again, we're going to need the molar mass of copper 2 nitrate. So here's grams, the starting given, which is of copper 2 nitrate. And we must be able to write our formulas out pretty well right now, comfortably and well and accurately. So the molar mass of copper 2 nitrate is 180, but let's just do the units first. So grams of copper 2 nitrate on the bottom, moles of copper 2 nitrate on the top. Noticing I'm labeling all my units of measurements. In 1 mole, there's 187.57 grams. Working that out, dividing those numbers together, cross-canceling my units to make sure, and then I get an answer of 0.5, and there's 4 sig figs here, so 5896 moles of my copper 2 nitrate. Okay. So that's type 2 problems, mass to moles. Now we go to moles to particles, type 3 problems, moles to particles. And it says right here, determine the number of atoms that are in 0.78 moles of mercury. And this is nice because it's it's an element. So we start off with 0.78 moles of mercury. And again, unit analysis, dimensional analysis, moles of mercury on the bottom, atoms of mercury on the top. And so in 1 mole of mercury, how many atoms are there? There's 6.022 times 10 to the 23rd atoms. And so multiply that through and you will get a pretty large number, which is 4.7. 2 sig figs, must be 2 sig figs as an answer, times 10 to the 23rd atoms of mercury. Okay, now we go to the 4th type. The 4th type of problem is where you're taking particles to moles. So you're going from particles to moles. The particles that we're looking at is formula units. And so I know that we're dealing with an ionic compound. So zinc sulfate is your ionic compound. So taking this, you start off with 5.40 times 10 to the 24th, and abbreviate formula units with FU, formula units, and labeling it zinc sulfate. And I'm trying to convert that into units of moles. So moles on the top, formula units on the bottom. And it's all zinc sulfate. So a mole of zinc sulfate has 6.022 times 10 to the 23rd represented particles, specifically formula units. So divide those two answers. You will then get 8.7 or 8.97 moles of zinc sulfate. Okay. Now we get to some multi-step conversions. This multi-step conversion, you're looking at converting grams of roses to atoms of roses. So let me show you this simple example, using this simple example. So we have 2.5 grams of roses. And we want to take those roses and convert it into units of moles first, because to get to atoms, you need to go to moles. Remember the mole bridge. So we start off with grams on the bottom and moles on the top. And this is the molar mass. So we have numbers we know we're going to put in. So labeling everything. So then we go from moles of roses to atoms of roses from there. And we're assuming that roses are single elements, okay? So here we have 1 mole has 3.0 grams using molar mass of a rose. And then 1 mole has 6.022 times 10 to the 23rd atoms of roses. Multiplying it all through, you get 5.0 times 10 to the 23rd atoms of roses. I would highly recommend working the calculations through so that to ensure that you end up feeling pretty comfortable with your calculations, okay? And by the way, I've been going pretty fast, but make sure you cross-cancel all your units as you go through your calculations. So let's do some chemistry calculations with multi-step. So if you look at this question versus this question, I put it on the same page so you can do some comparing and contrasting. You're looking at finding the moles of oxygen atoms in potassium phosphate, and then here you're finding how many oxygen atoms are in potassium phosphate, okay? So moles of oxygen here versus the number of oxygen atoms. So let's start off with this. Here we have 7.4 grams of potassium phosphate. And we have to convert this to moles. We're going to have to get to moles in order to get to moles of oxygen, right? Moles of any, if you want to dig into the moles of the parts, you need to have moles of the whole thing. So we take molar mass, grams of K3PO4, and then we put it and convert it to moles of K3PO4. Now, we know that since oxygen is in this K3PO4, we're looking at taking this moles of K3PO4, notice the units cross-canceling, and moles of oxygen on the top. And then we stop there because we have our moles of oxygen. So in a mole of potassium phosphate, there's 212.27 grams. And in 1 mole of K3PO4, there are 4 moles of oxygen, giving us an answer of 0.14 moles of oxygen in the end. Cross-canceling your units where you see fit, leaving us with moles of oxygen. Now let's go to how many oxygen atoms. So this requires just one additional step, and you'll see the additional step involves Avogadro's number. So it's the same setup up to a certain point. So 1 mole of K3PO4, and I'm going to go right to the conversion factors because I know it's the same setup here, following just the top conversion. There is 4 moles of oxygen to every 1 mole of K3PO4. And then now we take it one step further, and we're going to say that 1 mole of oxygen has 6.022 times 10 to the 23rd O atoms. Okay, we multiply it all, and you get an answer that's equal to 8.4 times 10 to the 22nd oxygen atoms, or atoms of oxygen. You can reverse that if you like. All right, this is the last problem, so let's go ahead and look at this last problem. We're looking at converting between formula units to grams of sodium bicarbonate versus formula units to grams of sodium ions. So we're digging into the sodium bicarbonate, into the sodium ion in the sodium bicarbonate in the second problem. So let's go ahead and look at the first. So we're looking at taking 1.8 times 10 to the 23rd. And since this is an ionic compound, you're going to see formula units of sodium bicarbonate. Okay, so we're first going to convert to moles because we're currently in formula units. We've got to get to moles. then the next thing is to go from moles to grams. So we can go from moles of sodium bicarbonate to grams of sodium bicarbonate. And the molar mass of sodium bicarbonate is 84.01. Looking that up on the periodic table, 1 mole has 6.02022 times 10 to the 23rd formula units. And so multiplying, cross-canceling and multiplying it all out gives you, you have to have 2 sig figs, so it's 25 grams of sodium bicarbonate. Okay, the same thing goes here. We start off with your given, always your given. Sodium bicarbonate. And then we work our way in the same light here, where you have 1 mole of sodium bicarbonate. That's 6.022 times 10 to the 23rd formula units of sodium bicarbonate. I'm going to squeeze in. I'm going to need some room. And then, knowing that 1 mole of sodium bicarbonate has 1 mole of sodium ions. So you're digging into the parts, so it's a mole to mole conversion. And then in 1 mole of sodium ions, there is, so notice I'm always tracing out my units, there's 22.99 grams of sodium ions. And so my answer ends up being 6.9 grams of sodium. I hope that helps. Please let me know if you have any questions in class.